Welcome to 11.2, day 1. Does the gummy bear brand matter? So now what we're going to do is we're going to be talking about the second type of chi-square test. So I'm going to go ahead and just go back to the first lesson. In this first lesson, we talked about the chi-square goodness of fit. So the goodness of fit test. In this, what do we notice maybe about let's go back to maybe our previous data. What do we notice about this set of data here? How many samples do we have? Well, to answer you, we have one sample and we have one variable, right? Well, in this new procedure, we're no longer going to have just one sample and one variable. Well, instead what we're going to have now is we're going to have 2, 3, maybe 4, 5, 6, 7 different types of samples. But again, still just one variable. So we'll have our one variable here, and that'll be just the color of gummy bear. And then our samples will come from the different brands that we have. So this would be our first sample, and this would be our second. And then we could use more and more gummy bear brands. But let's take a look. So in this distribution of gummy bear, or is the distribution of gummy bear color the same for Haribo gummy bears and Mahir gummy bears? We'll collect data as a class and determine if we have convincing evidence of a difference. So we don't necessarily know now what the distribution of Haribo gummy bear colors are, but what we're going to do is just say, is Haribo and Mahir the exact same distribution, or are they different? So in previous years, I went and I collected gummy bear data, and this here on the table, this is what we found as a class. So as a class, we found 29 of the Haribo were red, 21 green, 9 were yellow, 22 were orange, and 11 were white for a total of, let me add that up very quickly, and that would be a total of 29, or I'm sorry, 92. And then for the Mahir brand, we have 49 that were red, 38 were green, 28 were yellow, 26 were orange, and 20 were white for a total of 161. So now let's do the total number of reds that we have. Well, we had 78 total reds, 59 green, not caring about the brand, 37 yellow, 48 orange, and 31 white, and that gives us a grand total of 253 gummy bears that we sampled. So we used 2 samples here. We have sample 1 is the Haribo and sample 2 is the Mahir brands. All right, so let's go to question 2. How many samples do we have? Well, we just talked about this. We have 2 samples, and those are coming from 2 different populations. You have the Haribo and the other brand there. Perfect. So 2 different populations. So how many variables are we examining? Again, we're just examining one variable, and this variable would be categorical. So you'll notice when we're dealing with categorical variables, that's really when we know that we're dealing with the chi-squared categorical variables. So as a class, let's think of what the hypotheses would be for this. Well, the Ho would be that the distributions are the same, and we're going to test, are they different? So just to shorten it, I'll say the color distribution is the same. Then obviously you need context. And then our alternative is we're going to test the color distribution is the color distribution. This I just should have saved myself time. Just wrote it out. The color distribution is not the same for both distributions. Okay, now we will use a chi-square test to test if there is a difference between the 2 populations. First thing we need to do is figure out what are the expected values. So with the previous lesson with the M&Ms, we just figured out, okay, well, what's our sample size? and what was the company telling us the proportion of red should be. For this, what we need to do is we need to think of proportionately what are the expected amounts for Haribo and for Mehir if we're saying that the distributions are the same. So we didn't have the same number of Haribo candies as we did the Mehir brands, but we can proportionately try to figure out what we expected if they were going to be this. In our sample, what we want to do is let's write down our totals first in the columns. So the total number of red that we had was 78. We had 59 green, 37 yellow, 48 orange, 31 white. We sampled 92 Haribo and 161 of the other for a total of 253 gummy bears. And so what we're saying is we're not saying that we have the exact same amount of red Haribo as we do with the other. We're saying that proportionately we have the same. So if this is like 5% of the Haribo, or I'll think about it like this, like if 20% of Mehir the gummy bears are red, well then 20% of Haribo should be red, and so the sample would need to be 20% of 92 and 20% of 161. So we want to think about that proportionately. Well, the way you figure out that number would be, let's say we want to solve for the Haribo red to start. So Haribo red to start. Well, you figure that out by saying, okay, well, proportionately, how many reds do we have? Well, in our sample, we have 78 out of 253 gummy bears that are red. And then you'd want to say, that's going to give us some percent. And you just multiply that by the number of Haribo that we have, which is not 95, it's 92. And that's going to give us, what is that, 28.4 red. And so we're expecting 28.4 red Haribo, and then you can just do 78 minus 28.4 to give you the other brand, and that'd be 49.6. And so that's one option of doing it. Another way of really just thinking about it is you can think about it as the expected value for each of these is equal to the row total times the column total divided by your total, or the table total. So let's do another one just so we can see. So to figure out this orange right here, you'd say, okay, well, there's 48 orange total times 92 total Haribo divided by the 253. And so what you're really doing here is you can think of it as, well, what's the proportion of our distribution that's orange? That's 48 divided by the 253. Multiply that by the sample size, or vice versa. It doesn't necessarily matter, but this would be the format that you would do it in, which would give you 17.5. And you're going to do the same to solve for white, which would be 11.2, 13.8 for yellow, and 21.5 for green. And then you can solve for the other brand by just doing 39 minus 21.5. Or I'm sorry, that's not 39. That's 59. Which is going to get you 37.5, 24.2, 30.5, and 19.8. So we now know our expected counts for what we expect to get from our sample if the distributions were the same. And now what we're going to do is solve for this chi-square test statistic by just saying, well, how far is our expected value from what we observed? How far is our expected from what we observed? Our expected from what we observe, our expected from what we observe. So we're really just adding a little bit more for us to do now to solve for this chi-square test statistic. And so let's flip the page now and let's try to actually solve for this. So I've already filled out our hypotheses to sort of save a little bit of time, and to think about it, it's similar to our last hypotheses, and our Ho is going to be the color distribution for the two samples are the same versus, and that's going to be true for any one of these chi-square tests for homogeneity. And so that is what the name of the procedure is right here. So you have your hypotheses, Ho and Ha. We have our significance level of 5%. And let's go ahead and figure out what our conditions are. And these will follow suit with what the last conditions were, and that's going to be, we don't need to check for the independence, but we do need to check for random sampling. So we'd say we randomly selected the gummy bears, even though I know we didn't do that, but our last class did. We randomly selected the gummy bears. And then the last condition we have to check is large counts. Are our expected counts large enough for this data to be valid? Because again, we are not checking for normality, because most of our data should be close to 0, with a lot of our data or very little of our data starting to get far away from 0. Because the farther away you go over here, the farther away your expected values are from what you observe. So for large count, you say the smallest expected was equal to, or before I will say is, what would it be? It'd be this 11.2 right there. So the smallest would be white Haribo. Haribo is equal to 11.2, which is greater than 5. Therefore, all expected are greater than 5. So we've checked and checked. So because the smallest is greater than 5, we know all will be greater than 5. What I want you to do now is pause this video, and I want you to fill out the do and the conclude, and then try to answer this bottom question down here. Explain how this test is different from the chi-square test for goodness of fit. And we've kind of discussed this already, but I want you to give it a go. Okay, so in the do section, you have your specific formula, which is found page 1 of the formula sheet, and that's just going to be that the chi-square test statistic is equal to the sum of all observed values minus expected squared over expected. And so when you're figuring out what the chi-square test statistic is for this, you need to do every single observed value minus expected squared over the expected. That's including everything from Haribo red all the way to Mehir white. So 29 minus 28.4 squared divided by 28.4, 21 minus 21.5 squared divided by 21.5, all the way to here, plus all of these, and adding all that up, we end up with our chi-square test statistic of 4.134. And you can add in some dots in there to save you some time. Degrees of freedom. Well, to calculate this, you would do the number of rows we have times the number of columns and subtracting 1 from each. So we have 5 rows, and so 5 minus 1 is 4. We have 2 columns, and what I should note here is not including the totals that you create. Totals column / rows. So not including those. So we end up with the degrees of freedom of 4. We then find our p-value by going on to table C, chi-squared of 4.134, degrees of freedom 4. So go to degrees of freedom 4, and you'll notice that our chi-square would land somewhere around right here. So we know it's going to be a p-value that will be greater than 0.25. And so what I've gone ahead and done is I use my calculator to actually solve for this 38.85% p-value. Now you could really just go with p-value greater than 0.25, and that's going to give you the exact same result. So let's conclude on this. We'd say that since our p-value was greater than 0.05, We fail to reject Ho. We do not have convincing evidence to suggest that there is a difference between Haribo and the other gummy bear color distribution. So we do not have convincing evidence because we fail to reject. And what is the difference between the chi-squared test for goodness of fit and homogeneity? Well, for the chi-squared test for homogeneity, which is what we did today, we have two samples from two different populations, whereas what we did last class was the goodness of fit, and we only had one sample from one population. So, important ideas. You can pause the video here and copy these down now. Okay, so the first learning target, hypotheses. You have your ho and your ha, and these will always follow this similar style. You can write them using the word same or the word difference, but it's totally up to you. So you could say there is no difference between or no difference in the categorical variables. So there's no difference in color distribution between gummy bear or between Haribo and Mehir brands. Or you could say there is or the color distribution between the two is the same. That would be the same ho. Just it's up to you. I would just keep it the same all the way through. So there is no difference for ho, and then there is a difference for ha plus dot dot dot. And you only need to add context once for these hypotheses. Learning target 2 is the expected counts. So you need to figure out what do we expect to get for this entire two-way table. Given that the distribution should be the same, and to figure that out, you would do for this one here, you would find, well, what is the row total times the column total, and then you divide that by the total, and that gives you your expected value right here. And your degrees of freedom is the number of rows minus 1 times the number of columns minus 1. And the third learning target is sort of trying to differentiate between the two, because you run these tests the exact same. It's just identifying the correct one can be a little tricky for students. And here's hopefully something that helps you spot them a little better. And you have goodness of fit would be one sample, one variable. Chi-squared homogeneity would be 2 plus samples. So you could have Haribo, Mehir, Target brand, Vaughn's brand, etc. And then you only have one variable, color. So what I want you to do now is pause the video here and work through this check your understanding. Okay, so the first thing we want to do is state the appropriate null and alternative hypotheses. And so we have our ho and our ha. Our ho would be there is no difference in the distribution. Maybe I'll underline this. There's no difference in the distribution of response to the question when asked by male or female, where our ha is there is a difference in the distributions. And notice I really added a lot of context into my ho. And then for my ha, I can keep that kind of vague, kind of save myself time with my ha. B, show the calculation for the expected counts of male yes cell, then provide the entire table. So for the male yes cell, well, that would be the expected value would be the row total of 69 times the column total, there's 50 males, divided by the total number of people surveyed in this, divided by 100. That gives you the 34.5. And then you can fill out the rest of the table the same way. What's nice about this is there are an equal number of males and females, so their expected values are equal. So it's much easier to calculate it when they are equal populations or equal sample sizes. And last, we'll calculate the chi-square test statistic. It's not asking for the p-value, it just wants the test statistic. So it's observed minus expected squared divided by expected. So 30 minus what we expect squared divided by what we expect plus all the way to now the females 8 minus the 10 squared divided by 10, and that gives us 4.25.